So, hi everyone. So I'm going to be, as Emily said, talking to you about patterns of morphological disparity and how we might be able to explain those patterns. And so I'll gloss over this very quickly because I think most people in this room are probably aware of this distinction. But there's a fundamental difference between measures of taxonomic diversity and variation in form or morphological disparity. And so I'm going to spend this talk talking about morphological disparity, that is variation in form. And so I think it's really important to bear in mind when you're looking at macroevolutionary patterns or evolutionary patterns in general, that you can have very diverse groups with relatively low morphological disparity. And likewise, you can have really taxonomically rather poor groups that actually show very high disparity. And so thinking about disparity through time, there are really, I suppose, three kind of idealized models that we might think of when we think about how disparity within clades evolves through time. And so our naive view might be this, what I've called here the traditional model, which is a cone of increasing diversity and disparity. As a clade radiates or diversifies, disparity increases constantly, relatively constantly through time. Gould proposed an inverted model in which disparity early on in the evolution of clades, particularly of major clades, is much higher than it is subsequently. So this is the idea of a kind of winnowing out of morphological form through time. And then finally, Forty proposed this kind of modified version of that model, where disparity is high early on in evolution, but is maintained at those high levels. And so how can we go about looking at this in a more kind of rigorous and quantitative way? Well, the way that I've used and that other people have used is to try and generate disparity profiles. And really the methods I'm going to be talking about here have been done using character data, so discrete character data sets, because that's a way of getting good data on morphology for a large number of clades from the literature relatively easily. And you don't run into some of the problems about identifying homologous landmarks that you have with morphometric approaches. And so the aim here is that you group your taxa into that you have in your clade for a given cladistic dataset into time bins. You use some way of estimating the morphological disparity in those time bins, so carrying out a principal coordinates analysis of the character data using some metric, so I've used Euclidean distances, to estimate total disparity in those time bins, and then you can stack them to generate a profile. And then once you've generated a profile, it's relatively easy to apply very simple metrics to describe the shape of the profile. So, for instance, center of gravity, to work out, relatively speaking, when you're reaching high disparity. And so this has been done by Martin Hughes and others. And they essentially found that if you limit your analysis to looking at clades where you have the entirety of their evolutionary history, that is, they're not truncated by the recent or by a mass extinction event, that those clades are significantly bottom heavy. So they reach high values of overall disparity much earlier than you might expect randomly. And so that's very good looking, I should say, so Martin in this study was looking exclusively at various animal data sets, both invertebrate and vertebrate, a sample of about 98 different mainly extinct clades. And so what about other groups? So what about other groups of macroscopic organisms? Do they show a similar pattern? And so I did this with plants. And so these plots here are showing major groups of vascular plants. And you can see it's important to bear in mind the scale bars here. So diversity is in red on these plots and disparity is in black. And the scale bars are different for the different clades and for the different metrics. And so basically these are showing that diversity is increasing rather more constantly through time than disparity. And so we can say, yes, plant clades are showing early high disparity just the same as animal clades. And so how might we be able to explain this pattern? Well, one simple explanation could be that your total number of character states that you can evolve is somehow finite or limited. And this has been proposed by Pete Wagner in a paper in 2000, that you have character state saturation over the evolutionary history of clades. And so you could go from a scenario early on in the evolutionary history of clades where you have new character states appearing relatively frequently with each character state change. Whenever something changes morphologically, it's a new thing, to late on in evolution where you actually have a lot of recycling of character states. So you have a lot of reversals, re-evolving the wheel, as it were. And so could this help to explain the patterns in overall disparity that we're seeing? Okay, and so just to go into the method a bit here. So this method that Wagner used and that I used to investigate this problem really relies on getting a sample of phylogenies, reconstructing character state changes on those phylogenies, and then looking at character state changes along branches. And so what you need is a set of rules that you can apply to order your branches in your phylogeny so that you can produce a nice curve like this, where you're looking at the total number of character state changes on the x-axis versus how many of those changes are new things, new character states, new morphologies. And so on that plot, a line of 1 would indicate that all of your morphological changes, all of your character state changes are new things, are new states. And any deviation from that is providing an indication of character exhaustion, you're recycling character states. And just to say briefly that the primary way that branches were ordered using this process is stratigraphically, right? So you're ordering taxa by first occurrences and using that to order the branches in your tree. And then in the case of ties, you're also ordering by position relative to the root. And in the case of ties, remaining ties from that, the number of new character states that are evolving on those that are reconstructed on those branches. I can go into that in more detail for anyone who wants me to. But essentially, taking these character exhaustion saturation profiles, what I was interested in is developing some really simple kind of back of the envelope metrics to describe the shapes of these curves. And the two main ones that I settled on were really a simple threshold. So what are the number of character state changes on your tree that it takes to reach 50% of the total number of character states? So that's the top left plot there. And then the other method that I used was to try and estimate the total number of possible character states that you might predict given the rate of evolution by basically fitting asymptotic curves to the data and using that to estimate your kind of absolute maximum number of states, and then looking at the total number of states that you actually see in that clade as a fraction of that estimate. And so this is to show that this is those curves fitted to a number of the clades from the Hughes dataset, the Hughes et al. Dataset, to show that you see a range of clade shapes, but broadly the vast majority of them are showing some degree of character exhaustion. So they're all plateauing out, and you see this pattern in invertebrate, so arthropod, echinoderm, vertebrate, and vertebrate clades. And so while there are different shapes here, they're all showing the same broad pattern. And I should say that this character state saturation stuff has been published in an interface focus paper, so you can kind of go away and read about it in more detail if you want. But then what I was interested in doing is testing for correlation between these simple metrics that I devised and the point at which you reach maximum disparity in a clade, because based on the arguments I was making earlier, you might expect there to be a correlation between the two. and there isn't at all. So clearly, disparity patterns, overall disparity patterns, can't be explained simply in terms of the rate at which you're evolving new states. There is a correlation between disparity, how early you reach disparity, and overall levels of homoplasy in your data set. So it tends to be the case that clades that are re-evolving a lot of states do reach disparity earlier on in evolution, peak disparity earlier on in evolution than clades that are evolving new states that are less recycling of character states. But that's only in terms of overall homoplasy, not in terms of the actual rate at which you're saturating character states. And so I was slightly puzzled when I found this result, because it's not what I was immediately expecting. It's not a simple explanation. But I think I've kind of converged on a potential explanation for this. And I think it's to do with, you really need to look in more detail about how taxa are evolving their disparity through time and how they're occupying the morphospace. So here, I've tried to show two scenarios of clades where overall disparity remains relatively constant for much of their history, but they are clearly evolving clades that are actually, the total number of taxa is actually increasing quite significantly, and they're evolving new states throughout this period. So in the first case, which is shown on the left, you have the overall range of disparity is relatively constant, but the clade is moving through the morphospace over time. And so if you look at the bottom in the Ordovician, that clade really is occupying a different region of the morphospace than it's occupying even in the Devonian, right? And so through this process, you can continue to evolve new states, quite a lot of new states, while keeping overall disparity relatively constant. The other way that I think you can do this is in clades where they show early high disparity to the extent where subsequent subclades and taxa are essentially filling in the gaps defined within the bounds of that early radiation. So here you see a group that shows very high disparity early on, and subsequent taxa are evolving within those limits. And I think I can talk about this more, but I think there are potentially quite a lot of examples of both of these. So I think that ammonites show some evidence of doing this kind of moving through the morphospace. So do preapulid worms. And as far as the kind of second method goes, I think there's some evidence that angiosperms are doing that, and possibly various groups of reptiles as well. And so I think in order to explain patterns of disparity and the limits on disparity that we clearly see in so many clades, we have to turn to arguments involving constraint. It's not as simple an explanation as just looking for simple general patterns and correlating general trends. You have to look in more detail. I think the two big ones are classically discussed, of course, are intrinsic constraints and extrinsic constraints. And my personal hunch is that developmental canalization and ontogenetic constraints are actually, I think, really important in terms of explaining these disparity patterns. That's my hunch. So I've shown there the example of constraint in the number of cervical vertebrae in mammals. Most mammals have 7 cervical vertebrae. Sloths and manatees break the rule a little bit, but there's some evidence that in those taxa it's associated with deleterious pleiotropic effects, so they have higher instances of juvenile cancer and nasty things like that. But the same clearly isn't true of other groups of tetrapods, including perhaps most famously the plesiosaurs, which vary hugely the number of cervical vertebrae. And then extrinsic constraints, the idea that the number of ecological niches may be limited. And so if that's the case, then you might expect ecological release and concurrent increases in disparity after mass extinction or extinction events. I think there's some evidence of you certainly seeing that in crown mammals post Cretaceous Tertiary in terms of their dentary morphology. So just quickly to conclude, I think character exhaustion is common in animal clades, certainly in all the examples that I've looked at. But the amount of exhaustion varies significantly. Early high disparity seems to be a general evolutionary trend that we see in clades, but it's not explained purely by this pattern of character exhaustion. And so we have to investigate in more detail and look at ontogenetic constraint, developmental constraint, and also ecological restrictions. So thank you very much for listening, and I'd like to just thank these people who are the co-authors and my supervisors for the papers that I've been working on and put out. So thank you very much.